topics today is about amortized analysis, right? So before I tell you like what it is formally, we have seen a bit of this like last class in the event law tree already, when we try to analyze the total time instead of like a one single update time. Right? So that's basically amortized analysis. But today we're gonna go deeper. Okay, so let's start with a toy problem, right? When here I just have like, let's say that I write some number x in binary, and let's say I start x from 0, like here, start from 0, and I just keep incrementing x one by one, like on each operation I increase x by 1. And I said that the cost of this operation is just the number of bits that are flipped. For example, this operation takes one flip, so that's the cost is 1. This is 2 flip, so the cost is 2. And then 1 flip costs 1. 3 flip here, so the cost is 3, and so on. So like just a simple process. Okay. And suppose that I have n many increments. Can someone quickly tell me what's the worst case cost on each operation? How big can it be? Yeah.
It's like log 2 event, like however many bits there are, you're flipping all of them.
Exactly. Like the number, like this is gonna be log base 2 of n, just because like if you do n increments, there can be like n bits, log n bits, and like some of the time, like all the bits can be flipped. Okay, so that's the worst case time, the worst case cost. But now if we instead like analyze the total cost of the whole sequence, whole sequence of operations, then yeah, what do you think is the total cost? There is one direct way to see this. That is, I claim that it's going to be sum over k n minus 2 to the k. So why is that? Because if you focus on the k listed, the k listed significant bit, right? The k bit will be flipped after to the k operation. Like this bit, the least significant one will be flipped on every operation, but like the next one will be flipped every 2 operations. The next one every 4 operations, and so on. Right? There are n many operations, and the k bit will be flipped only after to the k, like time steps. So this, and then you just sum the cost that you pay for each bit. And here you can see that like this sum is a geometric sum that sum to 2n. Okay, so that's the total cost. And then it just means that the amortized cost is then like the total cost over the number of operations we have. So it's 2. Okay. So this is what I mean like amortized cost. It's just a total cost over the number of time steps. Like just like on average, how much do you pay per operation? Right. And you see, okay, for this simple scenario, you can see that okay, amortized cost can be much smaller. Like one is constant, one is something that grows over, like that grows as a function of n. Okay, so here is the definition. Like now I just try to, I think you get an idea what is amortized cost now, but I just gonna like go through it anyway. So like the cost, like when you talk about amortized cost, it makes sense to talk about this when there is a process that like there are some sequence of operations. And so this makes sense to talk about it when, for example, in the previous slide, when you keep incrementing counters, there are many operations. But you can talk about it for any data structures, for example. Priority queue that we learned, like that we looked at last time, there are like insert, delete, min, decrease key, like a some sequence of operations. Now you can talk about like what's the average cost overall of our sequence, right? So just think like the process that you have some sequence of operations, and suppose that there are k operations in total, and for each operation, let's say the cost at the ith operation is ci, then the total cost is just the sum of the cost, right? And you can say that like if the sum of the cost over k operation is something like c bar times k, then the amortized cost is c bar. That's the definition. Okay, make sense? Okay. And in contrast, like the worst case cost is not gonna be like a average cost c bar here. It's gonna be max of ci. That's the worst case cost. And you can see that like from definition, obviously, max of ci can be much larger than c bar, the average cost. Okay. It's important that like when like to know that when I say average cost, I really mean it's average over the sequence of operation. We still analyze the process in the worst case sense. Like we have like we try to get the worst case bound, right? But it's just average over the operation. It's not like we look at some random objects and look at the average and average the cost over some random inputs. Okay, so we still look at like some worst case sequence, but we average the cost over the number of operations. Hope you get this point. Okay. Okay. So, and just more generally, like there can be like the process, there can be like more than one type of operations. For example, there can be 2 or 3 and so on. Like for example, there can be insert and delete. And let's say that there are like a K1 many type 1 operations and K2 many type 2 operations. Then if the total cost somehow is bounded by like C1 bar times K1 and C2 bar times K2, then yeah, naturally we will like define amortized cost of type 1 operation to be C bar 1 and type 2 operation cost to be C bar 2. And the interpretation why we define it this way is just like you can think like on average, right? Type 1 operation kind of contribute to the total time by C1 for each time that you make type 1 operation. But like you can see that like what really happened might be like for some of the C1 operation, for some of type 1 operation, you actually spend much larger time. It's just that on average, when you look into the total cost, on average, it kind of contributes C bar 1 cost. Similar for C bar 2 for type 2 operation. Okay, so I hope that's clear. That's just the formalization of what is amortized cost. Question about this? Good. So now, yeah, and normally, like many times, amortized cost is gonna be much smaller than worst case cost. The question is just then, like, how can we bound this cost, right? And we have seen some way to do this. One way is just to directly bound the total cost, And we did this for for the incrementing counter that we just done. It just sum, look at the total cost and just try to bound that. And also eventually lottery that you saw last time, we just said that okay, even the whole look at the whole sequence of updates. The total cost is mn, so amortized over m deletions, the amortized cost is n instead of m. Okay, so many times sometimes you can do this, but sometimes it's just kind of hard to think about how to try to do this directly, and there's gonna be two methods that we will introduce to you how to bound amortized cost. One is bank account method. We will see this today, and the potential function method is for next class. Okay. So let me tell you what is bank account method. It's just really the way of thinking. It's kind of the trick of how to think about this. Okay, so how to think about this is to think financially. We actually have a good intuition about money, and we will use that. We will exploit that. Okay, so the idea is this. Suppose that for each operation, let's say you want to increment the counter. You imagine that you pay some money to bank account, right? You put deposit the money to bank account. Okay, and you might pay something in advance too. Okay, and then whenever there is some real cost that happen in the process, for each unit of the cost that occur, it's just gonna automatically deduce $1 from your bank. Right? For each operation, you don't care what happened. You just pay $C. And then for each unit of cost, that will just deduce the money from your bank. Okay, so think you have, this is you, and you just put money to the bank, and then there are some algorithm here, I don't know, yeah, some computer here, and it just keep deducing the money. Yeah. Okay. And then suppose that you can guarantee that no matter what, you never have deficit. The money is always positive on the bank account. Okay. Then you can see that the total cost, right, is just gonna be at most C times the number of operations. Do you see this? Right, because on each operation you just pay C to the bank, so the total money that you put to the bank is at most C times operations, number of operations, and on each operation, sometimes this algorithm might deduce the money more than C. Doesn't matter, but you know that at the end of the day, you have more than zero money in the bank. So it means that whatever you have paid so far is enough for the cost. Is this clear for you? Questions about it? It's too clear, right? Okay. Okay.
How is this different from the just total cost method or the direct method? Because it feels like kind of doing the same thing.
It's really kind of doing the same thing. It's you see the examples so that this way of thinking sometimes it's just more intuitive. Okay. Okay, but once the total cost is C, then you know that the amortized cost is C. Okay. So basically, if you know that on each day you just pay C, then you can just conclude that if you pay C on each day and you never get deficit, then the amortized cost is C. Okay, so let's see the example. Okay. So look at this toy example, like incrementing the counter. And what I'm gonna do is now I make sure that the bank account will have like a money of $1 per 1 bit. For each 1 bit, I put the money there. Okay, so like this. For each of the 1 bit, I have like a $1 here. Okay, and then we're gonna increment this number. Okay, so this thing flipped, so that cost me 1. But I also to maintain this invariant that I have $1 on each 1 bit. I also need to put money on this guy too. So basically this is what happened. Here actually I pay 2. I pay 1 to flip 0 to 1. I also pay another $1 to put the money here. Okay, think of this as like some advance payment that I pay to the bank. Okay, so here I pay 2. Okay. So let's look at the next step. This is when like something non-trivial happen. Okay. So if I increment the counter again, right? Then what will happen is like I want something like this will happen. Now, how much do I pay?
5.
Say it again.
5.
5? Well, not quite. I claim that I still pay 2. Still need to pay 2. Why is that?
Because you're using the $1 you already put on the ones to pay for the flip.
Exactly. Right. I still need to deposit just $2 to the bank because here I need to flip this guy. There's no money here, so I need to flip it. And I also need to pay advance payment here. That's 2. But everyone here that is flipped, my advance payment is paid for. Right? All the 1 to 0 flips are paid for by my advance payment. Okay? So you don't need to even think about this. Like you have $1 on it, so it's free. Okay. And you can see that on each day, there's just gonna be only 1 flip from 0 to 1. So like basically, I just gonna keep paying 2. Like next time, here I pay 2 because I flip this guy to this guy, pay 2. Next time, I pay 2 again because this is the one I flip, but for this one, it's paid for. Okay. So you can see that like this way of thinking sometimes is more intuitive, and you can see that every day I pay $2 at most. So the amortized cost is 2. It's kind of a shortcut way of thinking. Like you just think, okay, how much do I need to pay to the bank on each day? So that's my amortized cost. Okay. So in general, like there can be more than one type of operation. Like there can be 2 types of operation or 3, right? And if suppose that for each type 1 operation, we pay C1. Each type 2 operation, you pay C2. And similarly, like for each unit of real cost, each unit of real cost will deduce $1 from the bank. And if you never have the deficit, then you can deduce again that the total cost, the total money that you ever paid, is just gonna be at most this much. This is just the total cost is at most the total money that you pay. And so the amortized cost is just C1 and C2 respectively. Okay. So from now you can think like, okay, you just use this bank account method and just imagine that if this operation costs like for this operation you need to pay C1 to the bank, then you just deduce that the amortized cost for this operation is C1. If another operation costs C2 per operation to the bank, then the amortized cost is C2. Okay? So we're gonna use this. And in what context? We're gonna use this in advanced periodic queue. Okay. So we see last time periodic queue is just a data structure that supports three things, right? Like it contains a set of numbers, right? And first thing you can do with it is you can insert. So you can insert like item X with value K to the set. And next you can delete min. Here it will just find the item with minimum value and delete it from the queue and return it. Next is decrease key, which just decrease the key of X to something at most K. So we see this, we used it in Dijkstra, right? And like last time we used it in Dijkstra, and we using by implementing this periodic queue with binary search tree. So each operation takes you log in time. Okay. But today you're gonna see a better one. Okay. Like a first binomial heap that improve up the insert time to 1 or 1, and hollow heap that improve this to 0 or 1 2. Okay. So this is really nice and basically optimal. Can someone tell me why we cannot hope to improve delete min to 01 as well?
Is this where the min has highest priority?
Say it again?
Is this where min has highest priority?
Yeah, min has highest priority. Do you we know, right, that sorting, you can the best way to sort takes n log n time. You cannot improve upon that. Can you see if you assume that the best way to sort takes n log n time, why you cannot improve this?
I guess assuming we never insert or decrease key, if we're just constantly deleting min and we just had an array and we sorted it and went from right to left, it would still at least take n log n to get those n keys.
I don't quite understand. What can you
Erasing the concern to insert and decrease key, if you're literally just trying to find to be able to find the min n times, for the best way you could really do that is with a vector. You sort it and then you just go from the right to the right forward.
Okay, let's see. Maybe let me hear some other people. Okay.
Well, what I was thinking is if you assume that the best possible way to sort an array is n log n, if this was O1 for all three operations, you could essentially just keep inserting it into the binary tree in O of n times and deleting the min O of n times, and you get a sorted list at the end, which gives a sorting algorithm of O of n.
Exactly. Basically assume this as a black box that you can insert in order 1, and let's say also delete min in order 1. Then whatever set of numbers you have, let's say n of them, just insert each of that to your heaps, this black box heap that you assume that it exists. Insert all of that takes on in total. And if this thing takes order 1 too, then the total time you can sort this set now. Just keep deleting min. Right? Keep deleting min, you get the smallest guy, the next smallest guy, and so on. So that will take total order n if this is O1. So it means that you can sort any set of numbers in in ON. So that's impossible. Okay, good. This is when you assume that you do like, by the way, like the lower bound of n log n is comparison based. This is for comparison based algorithm, but you see that this algorithm that we discussed is comparison based as well. So that's why like you can improve upon this. Yeah. Lower bound is for comparison based algorithm. Okay. So this is really kind of optimal. You cannot hope to improve upon this, and we will see how to do it today. Okay. But just as a quick application, we see that this is useful for Dijkstra, so let's apply it, right? If assume this thing, let's apply it and see what we get for Dijkstra, the running time. Well, I'm not gonna go through the pseudocode, but you see that in Dijkstra algorithm, we're gonna like basically insert n times, and then delete min n many times in total, and there will be like we will call decrease key of m times. So like the total cost that you get is gonna be the number of times that you insert times O1. The total time that you delete times O log n, and this is amortized bound, right? We have log n amortized cost, but this is okay because we just look at the total time, and this is n here, this is n here, and we have there's gonna be m decrease key. Each of these takes O1. Right, we have O1 decrease key. So the total cost then is gonna be m plus n log n. So that's better than m plus n, everything times log n from last class. So then this is basically optimal if the graph is not too sparse. It's just linear time. So that's better. Okay. Not Fibonacci here. How long here? Okay, so we're gonna work our way through to get this heap. Okay. And I need some background. Okay, and the background is this. The first thing is to define what is heap order trees. So our priority queue or heaps, I will use these two words interchangeably, right? Heaps and priority queues, they are the same thing. Okay. So our heap will be a forest of rooted tree, and there's gonna be one item per node. And what I need is that I'm gonna maintain this heap order. That is, the parent is always like smaller or equals to me. Okay, like this guy is larger than the parent, and this is true for every parent-child pair. Okay. So this means that like the minimum key is always at some root of my forest. So that's the heap order tree. And also like a two heap order tree can be linked in order of one time. You can just link it like this. Like if you want to link these two guys, then this guy need to be the child of this guy. So you can link it like this. Okay. And you can do this, you can implement this in O1 using some like a linked list of the children. Okay. But I hope you can believe that you can link in O1 time. Any question about heap order trees? It's simple objects, right? Okay. So another concept I want to define is binomial trees. A binomial tree is just a tree with some special structure. Okay. So each binomial tree I have like something called rank, And rank 0, 3, rank 0 binomial tree B0 is just a single node. And then I'm gonna be defined like a rank I plus 1 tree in a recursive way, which is just the bi plus 1 rank I plus 1 tree is just rank I linked with another rank I tree. Okay. So if you from this definition, you can see that like the size of rank I tree is just 2 to the I, because like B0 is of size 1 and BI is just like the size of BI is just twice times the size of BI minus 1. Just to let you see it more clearly, like rank 1 tree is just rank 0, like 2 rank 0 linked together. This is rank 2. This is rank 3, rank 4, rank 5. Okay. So I guess you get an idea. This is how it looks like. And another way to see this is that like just an equivalent way to define binomial tree is that rank R tree is just going to be contains with one root node, and then it has like a children that with rank 0, 1, 2, 3 up to R minus 1. This is how the structure of binomial tree. And you can convince yourself from this picture too. Right. This is rank 6, one root node, and then 6 children. This is rank 0, 1, 2, 3, 4, 5. Okay. So, question about this? Okay, so now I'm ready to define what is binomial heaps. Okay. So we're gonna get to this one first. So the binomial heap kind of work like this. We're gonna maintain the list of heap order trees, like so have a forest of heap order trees. And also like so we have a forest, so the minimum guy is one of the root. And we're just gonna have a pointer point to the minimum root. Okay. Like this picture. You have a bunch of trees and you point to the minimum guy, minimum root. Okay. So that's the structure that like you're gonna have. And now I just need to describe how do I implement insert, delete min and decrease key. For insert, it's going to be simple. It's kind of trivial. Just create a node. Like if I want to insert item X with value k, I just create a node for this item X. Basically have a pointer from item X to that node U, right? And then set the key of U to K, and then add it as a rank 0 tree into the list. For example, if I want to insert item X with value 12, just create that node and add it to my my tree list. So that's it. Nothing much. And this is like a rank 0, so I put it into this 0 bucket. Yeah. And if I want to add another item with value 10, then just do that. Okay. And suppose that this value is 1, then what should I do? I need to do something more. Yeah.
You also need to update the min pointer.
Right. So basically, yeah, if this is 1, then I should actually, for each insertion, I need to compare, like the one that I insert and the min guy, right? I compare it, and which one is smaller, then I point to that guy. So if this is 1, then this pointer should be pointing to this guy instead. So updating the min pointer is easy. It's like a O1 time. So I assume from now that you keep updating the min pointer. Okay. So that's the cause of, that's like a insert, kind of trivial, right? Next is delete min. Okay. So what it would do is that, first of all, we kind of point to the min guy, so we just delete the minimum root. And once you delete the minimum root, we're gonna insert, like add all the children subtree to the tree list. And then we keep linking the tree with the same, rank until there exists only one tree per rank. When you link, the winner will increment its rank. And once you're done with that, you just find the new minimum root. Okay, so let's see example. We just gonna delete minimum root, right? So we delete that guy. We have a bunch of like a subtree from the children. We're gonna need to add all this guy to the tree list here. Okay. So I'm just gonna rearrange the slides a bit. Okay. And just add each of these guys to the list. The children here, like add it to the list here. This should be add to here, and so on. And now we just keep linking the tree with the same rank. So this guy have the same rank, so we link them. And this now has rank 1. It used to have rank 0. So this guy link. And when you link, you see that like the winner will be the smaller guy, right? 3 will be the winner because 4 is larger. And you put the rank here to be 1. And this guy have rank 1, so you move it to this rank 1 bucket. And then you continue. The rank 1 trees you link. And you try to link them here. So this tree will win. This one will win. So you link this and continue. And so on. Question about this? This will not stop, right? You need to, this now have rank 3, you move it to here and keep linking. So keep doing this until there is only one tree per rank. Yep.
Is it at most one tree per rank?
At most one tree. At most one tree per rank. Okay, so now you have like only one tree per rank at most, and then you just look at the roots, and then scan for the minimum guy, and it's here. Okay. So just some details like this bucket here. I think this is kind of an array actually. So that I can find like a rank I tree just by looking at the array at cell I, and each of these array at cell I maintain the list of trees of rank I. Okay. So with this, I can keep finding a tree to link. Okay. If I still can link them. Okay. Next is decrease key. Decrease key is simple. Like if I want to decrease key of item X to K, then like I just jump to the node U that like X point like that the item X point to, and then decrease key of U, and then swap up to maintain heap order. For example, like if I want to decrease key of X here, X point to this guy. I want to decrease to 4. Then I do that. Just decrease this to from 9 to 4. But now the heap order is broken, so I need to swap. So swap that and repeat until it's fixed. So here I need to swap again. So now I'm done. Okay. Is all the operations clear? Okay.
Yeah, x needs to be a pointer.
Say it again.
X needs to be a pointer.
Yeah, X is an item. It points to a node in the heap.
Okay.
Like think of X as like a vertex in your graph of Dijkstra, and this vertex point to some node in this tree in this heap.
Yeah, it's like insert return pointer or something.
Yeah.
Yeah, because otherwise, yeah. Alright.
Yeah.
This is for insert, but I mean, this is just a clarifying thing. For insert, the parameter x, it doesn't really need to be there. It could just be insert and then you put the value and in the function you could have create.
So I have X just so that like I think of a node in a tree and item X as some separate things. Like it's like a item X is something that you're gonna point to a node in the heap.
Yeah, but that could all just be handled in the function, right?
I guess so.
Well, like if you didn't give it a pointer and just a value and had it search for it.
So like I need this pointer so that like suppose I insert X long time ago, right? And now I want to decrease key of X. I need to be able to jump to this node.
Insert, I mean.
Yeah, for insert, like I need to maintain this pointer. I mean, because without this pointer, I cannot implement decrease key immediately. So, like for each item X, it kind of point to some node in the tree. If this is X prime, it point to another node in the tree. So now if I want to decrease key X prime, I can just point to this node. I don't need to search where is X prime in the tree. So this is why I need to point from an item to a node in the tree, so that I can implement decrease key. Make sense? Okay.
For like the child node that we changed, it made sense to like swap up. Don't we also have to like swap down? Like if we change like.
Yeah, we need to swap the pointers. Yeah.
Okay, yeah.
Yeah. Okay. All right. Okay, so now, so I hope you understand the algorithm, and the question is, I hope you see that at every time each tree is always have some structure. What's the structure of each of these three at all time? Yeah.
Heap order.
It's going to be heap order, that's one, but it has more structure actually. Scott?
It's like an unbalanced binary tree, right?
Unbalanced binary tree. It's not quite balanced,
Right.
yeah, but like there is some structure that we know that this kind of tree looks like. We just learned it actually.
Special structure.
Yeah.
Is it the rank?
Okay. Like so let me tell you, each of these three
Binomial.
is binomial tree.
Know what that means?
Well, okay. Do you recall what's the definition of binomial tree? Binomial tree is like the tree, right? Such that if this guy have rank 5, it's gonna have 5 children. This guy have rank 0, this guy have rank 1, and rank 2, rank 3, and rank 4. Okay, so you can see, I hope, that this really have like a rigid structure. Like, okay. Is everyone with me that every tree is binomial tree? Okay. And then like so now recorded the size of rank R sub 3 is just 2 to the R. So it means what? Now it means that the maximum rank will be at most log n. Why is that? Because there are just n mini nodes.
Yeah.
Right? And if there's some guy with rank more than log n, then there must be more than n nodes. Okay. And if you know that now you conclude that the maximum rank is log n. Also, you know that rank R binomial tree have depth at most R. Right? Rank 0 have depth 0. Rank 3 have depth 3. Rank 5 have depth like a 5. So it means that the maximum depth is also log n. Okay. So with this structure, you can now let's try to analyze the heap. Now let's try to analyze it. Okay. So let's look at the worst case analysis first for this guy. So what's the worst case cost for insert? Can someone tell me? Yeah, guy?
Constant.
Constant. Yeah, we just add some node, put a pointer there. That's it. Trivial. How about decrease key? What's the worst case cost? Yeah.
Logarithmic because it's logarithmic depth, which is logarithmic number of swaps.
Exactly. Thanks. What's your name?
John.
John. Thanks, John. Okay. Yeah, the time to decrease key is the depth of the maximum depth, which is log n. What's the worst case cost for delete min? Is it constant? Is it log n? How big can it be? Yeah, Scott?
I think it's ON, because like worst case scenario, you might have to keep reforming trees for every node, but I don't know if I can give like good justification.
Yeah.
What if all of the nodes are in rank 1 and you delete them in and then you need to regenerate?
Exactly. Like actually every node, like it can be order of n, and the reason is this. Like just imagine that you start from empty.
Rank 0.
Yeah, you start from empty and like there is like a rank whatever, like and keep inserting n times. For insert you do something trivial, just put everything in rank 0. But when you delete min, now you need to keep linking all this guy until there is only one tree per rank at most. So that takes ON. So that's bad, right? But now I claim that actually the amortized cost for delete min is good. So let's try to use amortized analysis, right? We're just gonna use bank account method, like design how to pay advance payment and without deficit, okay? And you're gonna wait, what? Okay. So we're gonna try to pay like say that we're gonna pay something for each of the operation without deficit, and conclude that at the end the amortized cost, the total cost is something, and the amortized cost is just how much we pay. Okay. Just the same method we just seen. Okay, so let's now try to use bank account method. Okay, and the invariant, like my bank account will be such that on each root there will be like $1 on top of it. So I put $1 on each of the root like this. Okay. And okay, let's see how much you, like if I want to maintain this invariant, how much do I need to pay to my bank for insert. So for insert, you can see that nothing trivial is going on, like nothing non-trivial. you just insert 12, so add that, and then I put another $1 here. So the cost is like 0.1 for the real cost plus $1 on top of it. So that's constant. How much I pay is just constant. Okay, that's easy. But now let's see delete min. Okay, for delete min, you're gonna delete this guy. Okay, so you need to delete like all of these edges, and also you need to put money. These children become the root now, so you need to put money $1 on each of these now. Okay, so that's the cost is like a log n real cost, because like a max rank, like this is the number of children is at most the maximum rank, which is at most log n. So the real cost is like log n, but also you pay log n advance payment here. Okay, so that's log n so far that we pay. But now we have money on each root, and now we need to link, right? What do? We link this, but we're gonna use the money on top of the root to pay for linking. So this link is free because we just use with this $1 to pay for linking. And the next link is free too. And basically all the links are free if we have $1 on top of it, on top of each root. Yeah.
Sorry, real quick. When we're linking the trees, it doesn't matter which value is chosen to be the root, and which one gets like right now 10 is the root of the first tree that you just made.
Yeah.
Does it matter which choice of the value, or no?
It just matter that if you wanna link,
They're the same rank. Like they're both rank 0 right now.
they have rank 0, and the one with smaller value need to be the root.
Yes,
Yeah.
but the choice of which two specific, they're just next to each other, is that?
Yeah, it doesn't matter. Like you can link these two guys. You can link whatever.
Thank you. Yeah.
But normally, like we maintain the list of trees in the linked list. So usually just link the first two.
Okay.
Link and so on. Yeah.
Okay, thank you, sorry.
Good question. Yeah. So you can see that with this invariant, all links are free. It's paid for by our advance payment. Okay. So once you are done with linking, you find a new root. You scan through this thing, but the maximum rank is log n. So that's another log n. So how much do we pay in total? Just log n. Right? We just pay log n in total. Although the worst case cost is small. Okay, for this decrease key, we just implement whatever we need to do. Just keep swapping. So the real cost is log n, the depth, but actually there is no advance payment we need to pay. Yeah, we don't create any new root. Okay. So the cost is we pay the real cost of log n. So you can conclude that now. Like you can see that this is like constant for insert. Log n for decrease key, and actually log n for the delete min. That's how much we pay to the bank. So you can see that, okay, with amortized analysis, we get this. Yeah.
How would you prove rigorously that your choice of the unit of real cost is equivalent to the amortized time, the actual amortized time?
Ask again.
So in this case, you chose each node in the ranks, the top one is the unit of real cost. How do you prove that that's a valid choice to prove amortized time complexity?
each. So you mean like how do I choose the invariant that I want $1 on each root?
Yeah.
This is like just like this is where the credit, like this is where you design it. Like you design that like that you want to have $1 on each root, and with this invariant, then you try to analyze like that. Okay, that you with this invariant that you have the $1 on each root. Now the cost that you need to pay per operation is now small. Like this is where like creativity, like you need creativity, like a wish where do you want to keep your money in on. Yeah.
So theoretically, you could have like any different ways of like.
Yeah. Like if you want to say that okay, you want gonna put $1 on everything here, every node, then maybe now like you need to pay too much. Yeah. So you kind of you design how to put money on this object so that you don't put too many money, and it's now enough to pay for.
So it was like part of that intuition, like two things, making sure that like you only assign the money like once during the step. It's like we only put money in when we broke up that first like tree and then put it on the roots, and we like save money by like linking them because they already have money on them. Are those like good points of intuition, like saving money and like only putting money in once during an operation?
Yeah, I think like one way how to design where to put money is this. You look at the worst case cost. You see when do you take so much time? This is when you link a lot, and you're gonna link only between roots. So if you're gonna link only between roots, let's put the money on the roots. That's like how to do, how one way I would do. Okay, so that's binomial heaps. Okay, let's now improve it to constant even for decrease key. Okay, right now when we decrease key, you need to like pay the debt. We don't want it even to pay that. Okay, so this is hollow heaps. So the idea is going to be similar to binomial heaps, but now each tree might not be a binomial tree. Each tree don't have that rigid structure. Okay. What we're going to do is like insert is going to be the same. Just do something trivial, add a node, and like have a pointer from item to that node. Nothing new. Decrease key will be very different. I'm going to tell you how different, but delete mean is similar. Okay. So let me tell you how to implement each of these. Insert is the same, so I will not go into it, but decrease key, right? So suppose that we have some structure like before, you have a bunch of trees and this list of trees, okay? And I want to decrease key of x to k. So what we're gonna do is like, we're gonna make, let's say u is a node that x point to before. I'm gonna make it hollow. I tell you what it means soon. And then I'm gonna make a new node for x. Like x gonna point to the new node instead. And this new node v will basically inherit all of the children of u, except the biggest two children. Like it inherit all children sub-tree of rank less than the rank of u minus 2. So it moves all the children of u with it, except that the biggest two children of u, leave it with u. Okay. And then set the key of v to like to be something at most k, like a decrease key basically. And then the rank of v is like the rank of u minus 2, except that you don't go below 0. Let's see example. Suppose that I want to decrease key of x, this guy, x point to this guy, from 7 to 6. What I gonna do? I create a new node. This is u, this is v. Okay. I create my new node and then move all the children of U to V except the biggest two. The biggest two is still with you. Okay. And the rank of V, this you still have rank 4. The rank of V is gonna be 2. And the key of V is now decreased from 7 to 6. Okay. So let's see another example. Next, okay, and also like this node, I claim it's now I declare it's hollow. In a sense, by hollow I mean it's just some node in the tree that has no item pointing to it. Like there is no item X pointing to it now. X is now pointing to this guy. Okay. And we can implement this thing like to move all the children in O1 real course just by like have the linked list of the children. Okay. You can think about this, it's simple. Okay, let's say another example. Suppose now I want to decrease key of X prime to 4. Can you tell me what do I need to do here? Yeah, just to make sure you understand. If I want to decrease key of this guy to 4. Yeah, Scott?
So you make it hollow and then you make a 4 that's a degree 1 tree and it takes the 15 with it, I think.
Yeah, exactly. We need to create like make this guy hollow, and then I'm gonna move all children except the biggest two, which is now just these children, to another and make another tree. And the rank of the new guys will be like from 3 is reduced to 1. So this is now hollow, and I make a new tree here. Okay. And then I continue. Now maybe I want to make this guy decrease the key of this guy to 9. So now like I just make this guy hollow and move all the children except the biggest two, but like this guy have only 2 children, so I cannot get any children. So the new one just have no children. Okay. And if I want to decrease key of this guy, so again, I get a new node here. This guy is now hollow and no children here. So you see how it works. Okay, good. So that's decrease key. Next is delete min. Delete min is going to be similar. First, you delete the min root, the guy that you point to. Okay. Delete it and add all the children to the tree list. Okay. But the new thing is that, okay, next you're gonna keep destroying the root that is hollow. Basically, delete that root which is hollow, and also add its children subtree to the tree list. Once you keep doing this, now you get like a bunch of trees where all the roots are not hollow, are full, and then keep linking them like before, and at the end find the new minimum root. Okay. So it's just this. You delete the min guy, and now these are the new roots. Okay, but these are hollow, so you delete this guy. These are now new roots. This is hollow again, delete it. And need to delete this guy too. You don't need to delete this because it's not a root. Okay. Just keep deleting the root that is hollow. So this guy you keep it. And now keep linking like before. Keep linking until there is just 1 tree per rank. Okay. Questions about the algorithm? Okay. So now let's analyze the structure of hollow heaps. Okay. Like the structure is now a bit weird, right? Like it's not binomial tree for sure because you can see like okay, this guy have rank 5, it has 5 children like before, but this guy have rank 4, but it has less than 4 children. It's not binomial heap for sure. Can we still say something useful about it? Okay. So and I claim that the structure is actually quite simple, like before. That is, the rank R node gonna have R children like before, except if that node is hollow, like this or here. If the node is hollow, then it's just gonna have like 2 children of the biggest size. This node of rank 4 will have children of rank 3 and 2. This node of rank 3 have children of rank 2 and 1. If it's hollow and have rank 1, it has like it just have 1 children, and if it's hollow and have rank 0, it have 0 children. Okay. So if I only have like this first invariant, then this is just the same as binomial tree, but now I have like this second property. That is like the guy that's hollow can have less number of children, but it's still gonna have like a biggest 2 guys. Okay. So now I claim that this is an important claim. Previously, we have that the size of rank R sub 3 in binomial tree will have size 2 to the R. But now this is not quite binomial tree, but I still claim something useful. That is, the size of rank 3 sub 3 will have size not 2 to the R, but like 1.5 to the R. So it still grows exponentially. So let's try to prove this, right? And we can prove by induction. The base case is true. Like rank 0 has size 1. Rank 1 sub 3 have size 2. So this is like a more than 1.5 to, like, this is more than 1. This is more than 1.5. So this is true, the base case. Okay, let's now try to improve, like try to complete the inductive step. Can you tell me what's the, like, how can you lower bound the size of rank R sub 3? Assume by induction, like use the induction. Can you tell me what's the lower bound of this rank R sub 3 using this invariant? Yeah, this is non-trivial, but yeah.
Is it either 2 to the n if it's not hollow, or like inductively whatever the size of r minus 2 plus size of r minus 1?
Size of, yeah, basically, you know that even if U is hollow or U is not hollow, it's gonna have sub 3 of rank r minus 2 and r minus 1. If it's not hollow, it has like everyone. So this guy have size at least basically the size of rank r minus 1 sub 3 and plus the size of rank r minus 2. At least, right? Because this guy will have whatever this rank of like r minus 1 and r minus 2. This guy is gonna have whatever like the size of rank 4 and rank 3. It might have more, but we just want a lower bound. Okay. And then by induction, this is at least what? This to the r plus 1, r point 1.5 to the r minus 1 plus 1.5 to the r minus 2 by induction. Okay. And then this is what? This is like 1.5 to the r minus 2 and plus 1. So this is 2.5, which is more than 1.5 square. So basically this whole thing is at least 1.5 to the r. So we complete the inductive step. Yeah.
Does it have to be basically when we picked looking at ranks r minus 2, r minus 1, is 2 the only value that works, or could you also do like r minus 3, r minus 2, r minus 1 and then get a similar result? You probably have to change the base of the exponential function.
Exactly. Like if you change the algorithm so that like right now the way I implement decrease key is that I move all the children except the biggest two. So if I change my decrease key so that I move all the children except I keep the hollow node, keep like the biggest three subtrees, then you're gonna you can say that like this is gonna be like the size here is gonna be plus rank of r minus 3 as well.
And then that would still work.
That would work. You're gonna get still something exponential. Yeah. By the way, like instead of 1.5 here, you can get something like golden ratio, like 1.58 something. But yeah. Okay. Anyway, like now you know that the rank r sub 3 has size exponential in r. It means what? It means that the maximum rank in our forest is going to be at most log n, but now base 1.5. Which means that the maximum depth is log n too. The maximum number of children is also log n with base 1.5. So it's a bit more than log n base 2, but within constant factor. And n here is the number of nodes, which is not quite the number of elements, not quite the number of items, right? Because we create some hollow node, but it's going to be bounded by the number of insertion and decrease key. That's the number of nodes. Okay, let's try to analyze this now. Okay. I gonna still have. We're gonna go right to amortized analysis, all right? And here is like the creativity. Okay, we're gonna decide where to put money, and we're gonna put money on each root, like before, but more than that. I'm gonna put $1 on each hollow node, and also its children. I put a $1 there too. Okay, so this is the invariant. This is a new idea. But with this invariant, now let's try to analyze the cost that I need to pay per operation. Okay. So for insert, nothing much, right? I still pay like constant real cost, and when I put a new node there, I put $1 on top of it, like before. So that's constant. Nothing interesting. For insert, it's just constant cost that I pay. The interesting part is decrease key. Okay. So decrease key, like when I point to this guy, and I make it hollow and move the tree here. Okay. The real cost so far is constant. Where do I need to put my money on? Where's the advance payment I need to do? Can you tell me the number of the nodes? Where do I need to put money?
6 because it's a new root, and then and then 7 because it's hollow and all of its children.
Right. So basically 6 here, 7 here, 8 and 9 here. Okay. So that's basically the cost is like a constant real cost and also $4 of advance payment. And this is the case for every decrease key. It's constant real cost. Move this and put money here, like $4, and keep doing this. If I do this decrease key here, move it and put dollars. There are already some dollar here, so I can have $2 here, but I just need 1. Yeah, I can pay a bit more. Okay, so this keep going. Okay, and put money. Anyway, you can see that with this invariant, the cost of decrease key is still constant. Okay. For advance payment, $4 of advance payment and constant real cost. But now the key part, delete min. Okay. So now know that I don't just have like a $1 on each root. I have $1 on each of these hollow nodes too. Okay, let's try to analyze it. Okay, I delete min. When I delete min, I create this root, right? I need to put advance money there. So like advance payment, how much do I pay? The maximum rank. That's like how much I pay, like log n. But now the next thing is keep deleting the hollow root. But I have money on it. So this is free. Each of the deletion of hollow root is free. Because I have money on it. And note that when I delete the hollow root, I create some new root. I create this guy, and then I delete this, I create this guy. These new roots already have money on it too. I don't need to pay. Okay. So now basically I need to keep linking like before. Keep linking the roots. When each root has the money $1 on it. So all these are free, are paid for in advance. So it means what? It means that the total cost that I need to pay is just like log n advance payment when I delete the root. But everything else is paid for. So that's it, we are done. We get an algorithm where amortized cost is constant for insert, constant for decrease key, and log n for delete min. Okay, questions? Okay, so yeah.
What happens if you call a decrease key on the minimum value in the tree?
Yeah, you could make it hollow and make a new root, but you could optimize that by just decrease that node, decrease the key of that node and do nothing. Yeah, like whenever you decrease key of the root, you can just decrease that key to optimize the algorithm a bit. but it doesn't matter. Okay, so here is some research question. Like we have learned some of the amortized analysis. But whenever you design some data structure with amortized guarantee, usually the next question is, can we actually make, can we de-amortize it? That is, when the bound is amortized, can you make it actually worst case?
I have a question on the previous slide.
Yeah.
For decrease key, don't we need to like refine the minimum key over all of the ranks or no?
You need to,
Change it.
yeah. When you decrease key, you might create a new root, right?
I mean like, do you have the pointer on what the current minimum over?
I know what you mean.
Yeah.
But you already point to some minimum. When you create a new root, just compare these two numbers and update the root, update the min root.
Okay, it wouldn't
So
be,
that takes like constant.
and it wouldn't be in any of the other ranks. It would just be in that one tree. The minimum value.
Yeah, because among the old roots, you know the minimum guy. Now you create just one new guy.
Yeah.
So you need to just compare to the new guy
Yeah.
to get the minimum one.
Okay.
Yeah. Okay. So my point is, whenever you get amortized algorithm, people can ask, can you make it worst case? And in this case, it turns out that the answer is yes. There is some data structure such that actually you get this same bound, and it's all worst case. It's really complicated though. So if you are interested, you can see the paper or look at the tutorial. But this so far is really simple. Like people usually teach something called Fibonacci heaps, which is the same guarantee here. When this is also amortized, not worst case. But they are like, it's more complicated. If you are interested, you can look at my video lecture from last year or like in YouTube. Yeah. But anyway, that's it for today. Next class is more amortized thing. Yeah.